on behalf of AIMS, I'd like to welcome you all to this evening's public lecture. And it's a special pleasure to welcome Professor Inez Fung from Berkeley, who is joining us for this event and will be the speaker for this evening. The Mathematics of Planet Earth 2013 year is dedicated to the role mathematics can play in understanding and describing our environment and our planet. And there will be many events all over the world, some of them conferences, some of them workshops, some of them special projects and summer schools. And this public lecture is part of one of these events, a series which will be hosted in 9 different countries. And we are very grateful that it has been sponsored by the Simons Foundation. They are supporting this and have made it possible. I'd also like to thank other people involved, especially our American friends and our AIMS colleagues who have helped to organize this event. Chris Marshall and Linda Kamara at the back there have done a lot in the last 2 days to make sure this got together. And of course, we're always pleased to have the public who are interested to attend such events. Our speaker this evening is Professor Fung, as I mentioned, from Berkeley, and she will be speaking on climate math. She received her training in applied mathematics and meteorology at MIT before joining the Berkeley faculty in 1998. She was appointed as the first Richard and Rhoda Goldman Distinguished Professor in Physical Sciences and also the founding director of the Berkeley Atmospheric Sciences Center. She has been studying climate change for the last 20 years and is a principal architect of large-scale mathematical modeling approaches and numerical models to represent the geographic and temporal variations of sources and sinks of CO2 dust and other trace substances around the globe. She has received numerous honors and awards, and among them, Fellowship of the American Meteorological Society, a member of the National Academy of Sciences, and she's been named one of the Scientific American 50 in 2005, and was awarded the World Technology Network Award for the environment in 2006. So we're very pleased to have you here. We're glad you've come all the way. I know it's your first visit to South Africa, and I know you've got an important story to tell us, and we look forward to hearing you. Thank you for joining us.
Thank you. Thank you very much. South Africa has always been a special place for me when I was a child studying geography. The Indian Ocean and the Southern Ocean and the Atlantic Ocean. It's a very special place, and I'm so glad finally, after all these years, I am here. I thank the African Institute for Mathematical Sciences for inviting me, and the Mathematical Sciences Research Institute in the US for helping make this possible. I've been studying climate for a long time. First, because I like the mathematics, I like the equal sign. There's something elegant about the equal sign. And so then I figured out, and I was in one class where they had a toy, and the water went this way, and the water went that way. It was a turntable that they took out of a professor's house, and they glued paper cups around it, and it turns out to be the Lorenz chaos model. But I didn't know. I just thought they had toys, so here I am. So it's fun. So I'm talking about climate math. And I spend a lot of time at airports, and what I do is look at satellite pictures. And this is a beautiful picture of clouds. And so I know how I can write the equations for this. I know the Reynolds number, and here's a flow. The wind is going this way, and there's an obstacle, and you have this beautiful Kármán vortices. And it's very predictable. Here they are at St. Helena. You can see the Kármán vortices this way. And this is Heard Island, and you can see the beautiful vortices. And the clouds, to me, always marvelous. I can't write poetry, but I can write equations about these clouds, okay? And so I can tell you all sorts of stuff about the clouds. The water vapor, the condensation, is a tracer of the motion. So it's marvelous. So what I'm going to talk about is not this. This is fun and elegant. But talk about weather prediction and climate prediction. The story began in 1922. Fry Richardson there's a book now, Weather Prediction by Numerical Process. And so he imagined, and there's a marvelous book. When I read it, it's very humbling. He's thought of everything. But the way he thought about the mathematics and how you solve the equations, not just the equations themselves, and you can read that. Imagine a large hall like a theater, except that the circles and galleries go right around through the space, usually occupied by the stage. The walls of this chamber are painted to form the map of the globe. Myriads of computers, that's people who compute, are at work upon the weather of the part of the map where each sits. But each computer attends only to one equation or part of an equation. The work of each region is coordinated by an official of higher rank. Numerous little night signs display the instantaneous value so that the neighboring computers can read them. Each number is thus displayed in 3 adjacent zones so as to maintain communication to the north and to the south. From the floor of this pillar, from the floor of the pit, a tall pillar rises to half the height of the wall. It carries a large pulpit on its top. In this sits the man in charge of the whole theater. He is surrounded by several assistants and messengers. One of his duties is to maintain a uniform speed of progress in all parts of the globe, and some of you may know of CFL criterion. In this respect, he is like the conductor of an orchestra in which the instruments are slide rules and calculating machines and people. So he attempted the first weather forecast. So this is the grid, okay, that he put over Europe. And so he wanted to predict pressure, temperature, and wind. So temperature changes the density. Density changes the pressure. Okay, so when you have two places with different pressure, then there's a pressure gradient. And so in the same way, wind goes from high pressure to low pressure, water goes downhill, we have wind. And so the wind from the north will bring in cold temperature, and from the south will bring in warm temperature, and here we go again. So the first forecast was not that successful. To calculate the pressure change over 6 hours, he predicted 145 millibars over 6 hours when the observation was much, much smaller. So nothing was done for a long time until 1950. And so here, a grid, so this is with Johnny von Neumann at the lead of the effort. So grid over the US, and they attempted to make 24-hour and 48-hour forecasts. It took them 33 days. This was done at the Aniac, at the Aberdeen testing grounds in the naval testing grounds in Aberdeen, Maryland. And so they didn't have 33 days, and they had to petition the Navy for additional days because they had not yet debugged the code. And so it's led by Jules Charney, who was my advisor, my thesis advisor, and I'll talk about how he figured out how to succeed where Richardson failed. Here, I like this. The Aniac has fewer than 10 words. Think about your cell phone. Okay, 10 words of read-write memory. And this is a function table, so this is like a thumb drive. Okay, a lot of them and a lot of wires. And to advance one step, then you have function tables. That's what is in memory, the size of the Earth, the rotation rate of the Earth. And then you have operations. So you multiply numbers. And then they punch out output. And then you have to organize the output because you only have 10 words of memories for the next operation. So the card reader was very slow, and they would dance while the card reader they would dance a jig while the card reader was reading the cards. And so it took 16 of these operations to advance one time step, okay? And so this is tough. You understand why it took them a long time to debug the code. And so what happened, why it was successful in 1950, number one is that we have computers, not people who compute, okay? And they made a 24-hour forecast for the US, very coarse grid, forecast in 24 hours on the very fast computer of the day. And not only that, they realized that the Richardson's numerical method was unstable, and they figured out how to make it stable. More importantly, the Second World War provided observations. So the initial state of the atmosphere was much better known. And not only that, instead of of using winds as the initial state, pressure is a scalar, and it's easier to interpolate scalar properties. And so, but more importantly, is the recognition that in the atmosphere there are all sorts of waves, fast gravity waves, and those are in their correspondence was like high notes in Chopin. Who cares about them? Okay, we care about the low frequency notes. Okay, so and because the atmosphere is only 10 kilometers thick, and the radius of the Earth is 6,375 kilometers. It's very thin atmosphere. So you can pretend it's quasi two-dimensional, and you can filter out all these pesky gravity waves, and so you can take much larger time step and accomplish that. Since 1950, we've got much. They don't even put this here. FLOP is a floating point operation per second. You can see how over time we have gone many orders of magnitude, much faster computers. But computers is not the only answer. We need better physics and better observations. So I'm going to talk about first seasonal forecast. You all know about weather forecasts. We observe the atmosphere sometime, the initial state of the atmosphere, and then we make projections, 6 hours, I look at but the error grows with time. We have imperfect observations, and we have an imperfect model. So there will be errors, and the weather grows with time, and so you know how the limit to forecast is. Okay, experimentally, I wouldn't look at 5 days, but we make routinely 12-hour forecasts and look at the errors in order to improve the forecast. We're trying very hard to extend that. But when we go to seasonal climate prediction, like El Niños, then we also do the same thing. Now we include especially the equatorial ocean, but it's a coupled atmosphere-ocean problem. We have also the initial state, what the atmosphere was like, but more importantly, the memory is in the ocean, in particular the equatorial Pacific, and so the observations put in the equatorial ocean. So then we have the initial condition, and then we carry the forward, even though we're going forward 15 minutes, 10 minutes, 5 minutes at time step. Okay, at the end we make a forecast several months in advance. So we have an ensemble. We typically do 50 or 100 calculations because there's noise. And so we take the ensemble average. So what we forecast is the statistics. It's the mean and the variance. We ask, next month, what is the probability that next month will be warmer or colder? And what is the probability that next month will be drier or wetter? So I dare not ask what will the weather be on my birthday. Okay, that's not good. Okay. Unless it's within the next 5 days. So I'll show you some results from here, from the Global Forecasting Center for South Africa. So you can see here in the coupled atmosphere ocean model, so here is the projection for maximum temperature anomalies, departure from normal for the coming 3 months, April, May, June. And so see fairly regular patterns, but this is fairly warm in Western Canada. And so from the coupled model, you can also forecast the precipitation anomalies, whether it will be wetter or drier in the next 3 months. So here, it will be a little bit wetter, and you can check next month, in the coming months. It will be slightly wetter, okay, whereas in these parts, it will be much drier, okay. So this is the probability. So from there, then from the global calculation, then we can downscale it. And so this is also from here, from the climate systems analysis group. So there you have the forecast. And so now instead of what the whether it's wet and dry, so you can downscale it to say whether it's normal, okay, whether it's wetter than normal or less rain than normal. You get a map like this, and again, here it's consistent, and this is a forecast issued several months ago. And furthermore, you can predict, and this is from the South African Weather Service, the extreme events, okay, because you have now an ensemble, okay, so you know, given all the random perturbations in the atmosphere, that from the multiple runs you can get the statistics of not just the average rainfall, but the extreme events. So, but it's one thing to forecast. What we always do is the verification. I'm happy when there's a discrepancy because now there's more puzzles to solve and then more stuff to do. Okay, but that's not that's me. But with the observations, this is a satellite observation of the sea surface temperature. Again, the departure from normal. So here is in these colors warmer than normal and cooler than normal. So then we can use this to check the prediction. But also we can use this to set the boundary, the initial conditions for the next round of forecasts. So these forecasts, the El Nino forecasts, are done by about 20 groups around the world. And so it's still in experimental phase, but we're very proud of the progress we have made. So you can see here, from satellite now, we have satellite observations for precipitation and also for the photosynthesis. Okay, so that again, this is a check. So it's always, for us, it's always you make a forecast and you say, what's the error? What's the error? You know, where can I work? Where do I need to work next? Okay, so we constantly, this loop of every month there's a new set of forecasts, and then you analyze the errors and try to improve as we go on. So now I talk about climate change. So we started here. I didn't go back to the 50s, but we started here in the 60s and 70s. It's atmosphere and the ocean. Okay, the ocean has a long thermal memory. So if I need to go forward, predict climate, I need to know who is remembering the weather for the climate situation for the last month, for the last year, and maybe for the last 100 years. So we are putting in vegetation because plants transpire water into the atmosphere. Plants have a certain albedo or brightness, how much sunlight is reflected from plants. So all of that, it influences the energy and the water balance. And so now we add in sea ice. And now what is exciting in the last several decades is that we're predicting the atmospheric composition. Okay, when we talk about climate change is the major cause of climate change is that the atmospheric composition is changing. 78% nitrogen, 21% oxygen. But the little guys, okay, the CO2, all the little substances, the trace constituents in the atmosphere are changing, and it's those little guys, the aerosols, suspended liquids and solids in the atmosphere, that the sulfate aerosols reflect sunlight, dust can absorb sunlight or absorb energy, and then carbon cycle, obviously the CO2. Plants take up CO2 and decomposition returns CO2 to the atmosphere. CO2 goes into the ocean. There's the chemistry and the biology. So to know what the CO2 might be in the atmosphere, now we put in the carbon cycle. And so we now have nitrogen cycles and phosphorus cycles because, one thing leads to another. Okay, so etc. So we have expanding these capabilities. So now we call them Earth system models. So we predict all these things. And now because of faster and faster computers, they now come not the whole grid that you saw for Richardson, but much, much finer resolution for the whole globe. And so I did a calculation then. And I added interactive CO2, and it took 6 months. I did a 1,000-year run, and I was an absolute nervous wreck because it was on the computer for 6 months, and it goes up. And I said, "Did I make a programming error? Did I do?" Okay, but everything worked out. Okay, but it's for me it's really fun, even though when the code is running is. I'm a nervous wreck. Okay, so climate. Okay, so we have CO2. Okay, we know when we talk about climate, you talk about. I'm asked all the time, what will the temperature be? I'm going back. Okay, so why is the climate changing? Okay, the climate changing and the way we talk about it is there's a forcing. Forcing is what we're not yet captured. So if you look at the ice core record, and this is from the Australian ice core, very high resolution ice core. This is 10,000 years ago and to present. Okay, so CO2 has gone up. It's about about 250 parts per million. That means if I go out and grab 1 million molecules of air from the air, I get 780,000 nitrogen, 210,000 oxygen, and I get 200, okay, not 200,000, but 200 molecules. Of that million, I get 250 molecules of CO2. Okay, and it's slowly increasing. Methane, and so CO2 is a greenhouse gas. You know what a greenhouse gas is? It absorbs, so CO2, this is CO2, okay? So CO2 can do this, okay? It can do that, okay? So the right wavelength, okay? It's my wavelength, then it gets into an excited state. And so then the energy, instead of escaping to space, is trapped. I mean, it's not trapped. I mean, we say trapped, but the CO2 is going crazy. Okay, so when I look at the atmosphere, there's the CO2 going around. And methane, think about the molecular structure of methane with four hydrogen it can do. It has more degrees, it has more excited states. Okay, so methane, even though this is measured in parts per billion, CO2 is measured in parts per million, this methane is a much more effective greenhouse gas. It gets, there are fewer of them, but they get very excited. Okay, so similarly for N2O. So if you look at so what we can do, because we know from physics, from quantum physics, where the absorption lines are, that means where at what wavelengths, how CO2 absorbs, so we can transfer that into a heating rate for the surface. Okay, so we convert the concentration, the mixing ratio, to a heating rate. So then we look at, so for CO2, remember what I said before, the concentration of CO2 in the atmosphere was 200, in the pre-industrial was 270, 280. This is when Dave Keeling went up to Mauna Loa, Hawaii, and so you can see the increase in the CO2 in the atmosphere. It's gone up by 30% since the records began. Okay, so think about all those excited molecules in the atmosphere. Also, in the CO2, not only is it increasing, you can see a very regular cycle, which is the photosynthesis. This peaks in about May, and so the photosynthesis starts and the CO2 is removed from the atmosphere, okay, and then decomposition returns the CO2 to the atmosphere. So this is a beautiful record of the breathing of the planet. Together with the CO2, we have a very temperature record, very good temperature record. This is a thermometer we call the instrumental record. It's a thermometer record. And so you can see from 1880 to the present, you can see how globally average temperature has changed. And I drew the line here for when the CO2 record started, in the late 1950s, and you can see how globally average temperature has increased. So every year we say, the warmest years, the 9 warmest year was in this period, the warmest 10 years are in this period. So every year, so you can see the steady increase. It's also worth noting that, yes, there are periods when the temperature goes down, but you see the long-term trend and not just the year-to-year fluctuation. So when we have CO2, so we have CO2, methane, all the increases in the atmosphere, then I have an initial warming for the surface. So what happens is that when it's warmer, there's more evaporation from the ocean. Now water vapor is another greenhouse gas, and there's a lot of them, and they get very excited, many degrees of freedom. So water vapor, more water vapor in the air would enhance the warming. Similarly, when we decrease snow cover, when it's warmer, the snow melts, and so it makes the surface darker, and there's more absorption of sunlight, and so it also contributes to the warming. We call this positive feedback, but I was told positive feedback is a good thing. Okay, we don't want this. Okay, so this is an amplifying effect. Okay, so if we warm, we evaporate more water vapor, there's a likelihood that we increase cloud cover, and so the cloud cover would be bright and reflect sunlight, and so this is the absorption of solar energy, and so this may be the dial in the climate system. So that's why I'm focused on clouds, okay? Am I going to have more clouds this way? I'm from the tropics. I like cumulo, those clouds do different things from the clouds that rain on me in California. So we spend a lot of time on clouds because the dial is right there. So here is a climate model projection. And so from the National Center for Atmospheric Research, the people I've been working with for quite a while, so this is relative, 0 is relative to the average 1870 to 1899. So you can see this is the regional temperature change, and here is on the bottom is the globally average temperature. You can see when Krakatoa went off, there's a dip in the globally average temperature, and then you can follow the various volcanoes going off. The point here is that even though we talk about global warming, it is not uniform. Okay, there are always patterns, there are weather patterns, and so it's not yet. I mean, now here there's the weather system takes over, and so here Agung went off, El Chichon went off, and Krakatoa is going to go off. Pinatubo. So you can see now we're in 2007. Now it's here. Okay. So what we have here are several scenarios. A2 is a very aggressive fossil fuel emission, energy consumption scenario. A1B is more conservative, and B1 is a more planet-friendly scenario. And what we also have here is commitment. Commitment is if the CO2 stayed at the level of 2000, okay, we're not increasing by some magic. I'm the emperor of the universe. So the CO2 stayed. The CO2 that is emitted today, in the atmosphere already today, is still warming the ocean, is still causing evaporation, and the water vapor, all of that, the water cycle is going to take over. We still would be melting glaciers and melting sea ice, and so that feedback is going to continue. So even though we keep the CO2 constant, stop the emission, then there's still a committed warming. So you can see here, globally average temperature is 4 to 5 degrees higher. It's always painful for me to say that, well, we were wrong, not about this curve, but we were wrong about the scenario. What we have seen in the last decade is higher. The emission, the fossil fuel emission is higher than what we thought would be the most aggressive emission. So we expect a temperature much higher than this. The other question I always get is, CO2. When I go back to the current the thermometer record, I'm always asked, well, isn't it natural causes? Well, it could be, but when you look out here, I don't think we need to discuss. Okay, the CO2 forcing all the greenhouse gases, the methane, the nitrous oxide, all of those are going to overwhelm what the natural causes here. So with the model, you can also test hypotheses. So this is from the last IPCC report. And so you can see so this is the swarm. So all the countries, for the United Nations, the Intergovernmental Panel for Climate Change. So now we have a protocol, all countries that have a climate model, these are the experiments we want you to run. These are the output, and please send all your output to this particular place so that everyone can analyze your output. Okay, so the swarm of orange lines is the calculation by each model. And the red line, the thick red line, is the average of all the models, and the black line is the observation. So you can see when we included all the forcing, the greenhouse gases, the solar variability, the volcanoes, we have a reasonable match to the observations, whereas if we left out the greenhouse gases, then there's no way we can explain the recent warming. This is inconsistent with other. Okay, so we not yet. There's no way. There's only one atmosphere out there. I cannot repeat that atmosphere out there. I can only repeat it in the model context, and so there's no. It's very difficult to say this is exactly the cause. Okay. But this is why we say we are very, very sure that the climate warming is due to the increase in greenhouse gases and due to human activities. Now I want to change the topic a little bit. You're familiar with the snow in Johannesburg last year. And in North America, my mother lives in Vancouver. There's the Winter Olympics. Okay, they had to truck in snow, helicopter in snow. Whereas at the same time in Washington, they were paralyzed with the snowstorms. They don't know how to handle snow. So snow is falling in the wrong places. And this week, it's snowing in England. They were in Great Britain. Whereas the same week in France, in Nice, people on the beach. So there's the dramatic changes in weather pattern. And I can recite to you all the weird things that have happened, tornadoes where we don't expect tornadoes, and fires here and floods next door. So what's going on? You know, when I talk about snow, I mean, I'm talking about global warming. Okay, why should there be more snowstorms when we're talking about global warming? So what we note from the observations is that there are pressure oscillations. Okay, here between the South Pole and between Antarctica and the continents, there's a pressure oscillation. Okay, sometimes this is the index. So sometimes it's higher at the South Pole, and sometimes it's lower at the South Pole. And remember Richardson. So when I have a pressure gradient, then we have stronger winds, and so that changes the weather pattern, etc. So we're finding that there's an increasing trend in this index. And so one of the questions is, this is spatially coherent, but it's not regular in time. There seem to be changes. And in the northern hemisphere, we have the same thing. We have the northern annular mode. Again, it's a pressure. It was first discovered as a pressure oscillation between Iceland and Portugal. So there again, so sometimes that pressure difference is stronger and sometimes it's weaker. And so whether it's stronger or weaker would say what the storms that go to Great Britain, okay, whether there's stronger winds or weaker winds. And you can see now it's very negative, it's very strong winds. Okay, so again, it's the abrupt change. So can we look at these abrupt changes? I don't know how. So I had to go back to Lorenz, and I think many of you know the chaos equations. Okay, what he wanted to do, he was a meteorologist. He wanted to say the atmosphere is not linear, and you cannot use linear regression to predict. Okay, so he was trying to find a set of equations. Okay, so what he came up with is this is a fluid, and you heat it from the bottom, and that's the parameter R, and we fix the scale B. Okay, so it goes this way. You expect convection because you're heating from the bottom. Okay, but sometimes it goes the other way. Okay, so this is X I'm going to show you is positive one way and negative the other way. And so the crux of all of this is once I know enough heating and I fix my scale, then it's the property of the fluid. It's the ratio between the diffusivity and the viscosity. So the viscosity is given a certain amount of heating, how fast would it go? Okay? So molasses, okay, would be slower. And the other one, the diffusivity is while it's going around, how fast is it losing heat? Okay, so when it gets to the other side, is it going to sink? Okay, or is it going to go back? Okay, or the convection from the bottom will overwhelm it and go the other way. And that was what drew me to this field a long time ago when this little toy that we played with. So you can see here I'm plotting X and the vertical temperature gradient, and 0 is here. So this side, you can see it goes one way, okay, on the right-hand side, and on the left-hand side, it goes the other way, okay? So I think many of you have played with these kinds of movies before. So what I did was I took 10 of these, okay, slightly what Lorenz did, very close together, 10 of them. And so here are the 10. So you can see at the beginning, there are five time steps. All 10 of them hung out together. Okay, and this is the weather problem. Okay, so he wanted to show people that you cannot predict the weather beyond that. Okay, so it goes crazy after that. So when we look at climate, then climate is the average, right? I said the statistics. So now we can look at this. And this is the mean of the 10, the average of the 10 lines. And so here is the average, and it's fairly stable. It's a fairly stable climate. And for climate people, that's just a spin up. The weather people stuff. Okay, we don't look at this. This is for the system to adjust to itself. And so you can also do the statistics of this so that you find there are two stable climate regimes. Okay, it's a very clean model to look at the system. So can we predict the regime change, okay, from one side to the other side? So this is Eugenia Calne. She's from Argentina, and she was the first woman PhD from the MIT department that I was in, from Charney. And so what she did with her students was to say, you stretch out what I had in the blue line, you stretch out here. So every so often, you introduce a perturbation. You kick it, okay? And see whether the perturbation grows, okay, or it damps. So you can calculate the growth rate, okay, of the perturbation. Okay? So what I have then is, here is x again, whether a positive is looping one way and negative is looping the other way. And here is the growth rate calculated. So I've colored in green when it's damping, when the perturbation just dies away, and yellow is minor growth rate, and red is very fast growth rate, okay? So now I can show you the same curve, now not in blue, but with all the growth rates colored in. So I want you to take a look at it, and can you come up with a rule for when it goes through when the circulation changes side? Anyone notice a pattern here? So what I'll do is to stretch it out. Okay, so this is, again, the stream function. Positive is going in one direction, and negative is going in the other direction. You can see when there's a string of red, very fast perturbation growth rate, there's some indication of a transition. So if I stretch it out again, the first 500 time steps, this is a little run of red. No. But when we go here, okay, then when we have a long run of red, then we go change direction. Okay, when we have a long run of red, we change direction. Okay, again, you can see this. This is when it sits there in that little loop. Okay, doesn't go anywhere. Again, a long run of red. Okay, so we can look at this. It's really fun to play with this. Okay, so you can see this. And Lorenz, this is a very famous, could the flap of a butterfly's wings in Brazil set off a tornado in Texas? And Lorenz says it depends on the stability of the atmosphere. But what Eugenia Calne and her students have done is to set up the rules that when there's a fast perturbation growth, those are the red lines, and a long string of red lines, of red dots, then the next orbit will be the last one in the present regime. And how long it starts in each regime, then when there are fewer red stars, then the next regime will be short. So this is the beginning. We haven't got it to the global model. We're just learning how to think about these abrupt transitions. And this is an impressive skill, okay? So what I did then is to say, suppose we have climate change. So this R is the heating at the bottom of this fluid. And now I increase R, okay? And you can see now the X, the stream function, is increasing, the average of the stream function. So it's going faster and faster. It's changing directions also. And so this is the standard deviation. That means this is the weather, okay? The weather you can see the standard deviation is also getting bigger. Okay, the weather perturbations, the weather is getting weirder. Okay, this is how I look at it. So now maybe we are in the early regime, okay, where there's snow is still possible. So when it's getting the weather, the jet stream is going like this, okay, then we bring cold air from the north. Then we have snow, but when we get into the red, you remember the movie, when we get into the red space, there may not be much snow. So here is the same diagram, but this is for the standard case, and this is for the ramped up heating case. And you can see there are much more red dots, and so we do expect a lot more chaotic transitions, okay? And so now what we're doing is to translate this to the global context, in the global model, not just in a marvelous toy model that we love playing with. Very elegant toy. I hope I've shown you that the atmosphere is marvelous puzzle for me anyway. I look at cloud pictures all the time, and it's just beautiful, beautiful pictures, organization of clouds. The key to the climate prediction, to weather prediction, to seasonal climate prediction, and to longer-term prediction, obviously is the mathematics. I wanted to show you all the equations, okay, and how we solve them, but you get the idea, okay, that all the equations and then the observations. Observations is utterly critical because nature's smarter than all of us put together. There's always a surprise. When I think we've done very well, then nature does something else. Okay, so we want the observations to know how the weather and climate is changing, because we're heading into a climate regime where there's no prior analog. We have not seen CO2 this high. We have not seen temperature, nor the rapid rate. I mean, what distinguishes us from the past warm periods is the rate at which the CO2 is going up, okay, and the temperature is going up. It's at something at a rate that we have not seen before. And so the key is also the new application of physics, chemistry, and biology to understand how plants would do in a warmer world, maybe a drier world, or maybe a wetter world somewhere else. Higher CO2, whether the plants will grow more, whether there's enough nutrients to support the plants, and other things. And so I hope I have persuaded you that climate change is happening now. There's present, what has happened, there has to be a component of the natural cycles. You have the El Nino cycles, 2 to 7 years. I showed you the northern annular mode and the southern annular mode, very crudely maybe decadal-ish type cycles. And underlying that, we expect 100-year cycles and 1,000-year cycles that we do not have records long enough to articulate with confidence. So, but it is changing, and the projections, I think, are very clear. We know there the CO2 is doing. It's excited. The more CO2 we get put into the atmosphere, there's going to be more excited, not just CO2, but because of the feedback, water vapor is coming in. Okay, the helper is water vapor. So then there's warming, and so with all of that, there is the changes in the wind pattern and in the wind pattern, in the temperature, and in precipitation. So we do, from all the models, we do see intense rain. When it rains, it's much more intense, and the drought periods are going to be longer. And that, I think, we have already seen in the weather record, in the existing record, not just in our projections. And more extreme weather, that is, I kept saying, oh, we made the first projection of this in 1980 something, okay, that it will be more extreme weather. But we don't know. What we're working on now is to get more realism and more resolution in terms of information that we can present. Scientific challenge. Obviously, there are many. I put this cloud up because I can't write equations for this thing yet. Okay, so there's evaporation of the raindrops along the way, etc. So what we're doing is multi-scale modeling. Clouds, when you look at clouds, the clouds are maybe several meters. the model, even with the super fast computers with a lot of memory, the finest grid we've got for these long runs may be now down to a quarter of a degree, maybe 25 kilometers. Okay, so there's no way we can capture clouds. So we have clouds, fine, very local, regional, very short time scale, cloud resolving models, and we have other multi-scale, how we deal with clouds, different kinds of clouds. I love, my favorite, my cumulonimbus clouds, and the billowing, and all the beautiful clouds. And what we're also doing with data assimilation, I'm doing a big project using Kalman filters. So we're assimilating using satellite CO2 data and raw weather data, and trying to do that to fill in. The satellite goes around like this, and the Earth is rotating underneath it. So you basically have a noodle of information, okay, like a yarn you're wrapping around. And you want to make a map, okay, so you have to fill in where the satellite's not seeing. And so this is a major undertaking by the entire field, is how do you bring in all the different satellites, different orbits, different resolution into the climate model, so that we can advance our projections. And what I showed you is dynamical systems. We're looking at what are the abrupt transitions, the thresholds, the tipping points. And so this is going into a space that we know we're beginning to learn, but this is at the early stages. And also the statistics. How do we characterize the uncertainties? I showed you the swarm of orange lines, okay? The uncertainty only captures what we think we know, okay? And so how do we characterize, use the statistics to do risk and uncertainties? I'll end with this figure. I talk about the mathematics. I talk about the things that are fun. But it's a societal problem, and this is what keeps me up at night, not just whether the code is running or not. There are two energy problems. I'm not advocating not using energy. I have iPods, I have a washing machine, I use energy, okay? That defines the standard of living. But what we're using, fossil fuel, is the remnants of biological material that didn't get decomposed, okay, in the ocean or in wetlands, okay, or in peat bogs, in the tundra. And so it's using that sunlight from over 100 million years ago. So right now we know 1.6 billion people on Earth have no access to electricity. 2.6 billion people use charcoal, biomass, agricultural residue as their primary energy source. So that's why I talk about the two energy problem. One is the energy because our consumption of fossil fuels is changing the climate. But there's also the other problem. The other challenge is not problem. Challenge is decarbonizing the energy so that we go to using renewable energy, and I think of using the newer sunlight, okay? The sun that's out there, we should take advantage of it. So we have solar, wind, again, the differences, pressure, temperature, pressure, changes in cost, the wind and hydro, biofuels and other things. So I want to say, especially to the young people, that I'm hopeful. I'm not somebody to say, something horrible is any. We went to the moon. Okay, Watson invented the steam engine. We have airplanes. We have breakthroughs. We have the internet. You have iPhones. You don't need landlines anymore. So I look at this and I look at all the young people. The future's in your hands. It's your future. You can blame your parents, but they didn't know. Okay, but they didn't know. Now you know, okay? So the future's in your hands, and I am very optimistic that you will figure out what to do. So thank you very much.
We will have time for questions, and we've got 3 roaming mics. And we've got 3 people assigned to them. Now, when you ask a question, please speak into the mic because it's been recorded, even though you think your voice carries. Okay, thank you. So we have time for questions. Any questions, please?
what does the ideal computer look like for running these simulations?
You're asking a very difficult, open-ended question. I think that there are multiple levels. First is the conceptual level. That's why, I still play with the Lorenz 3 equations, so I know how to think about it. At the computers, you see, the computers are going to get faster and faster and faster. There are going to be more processors, and we can go to higher and higher resolution. So a lot of the computer requirements are dictated by the information requirement. I'm not into running it at super high resolution for 1,000 years. So where we are at is asking the users of the information is to what level do we need to predict precipitation for a country or for a small area. For municipality, it's very difficult. I mean, can I do San Francisco? No. Okay, they want me to predict San Francisco. I said, not yet. Okay, but this is where the multi-scale model comes in. You have the global model, and then you go into smaller and smaller regions. And so you take into account all the little mountains, okay, and the little valleys where for Los Angeles where the Santa Ana wind comes, and all of that. So I would not. We will have faster and faster computers, and I'm sure that we will take advantage of the next fast computer. But I think that it's not just a computing issue. It's what information do we want out of that. And so that would dictate what computer I would choose. Does that answer your question?
Yeah, kind of. It was more sort of exchange of information between cells the bottleneck, or is pure sort of raw computation the bottleneck?
The bottleneck is even though I show the flops, the floating point operations per second, it's the exchange. It's exactly that. Richardson really had it right. Richardson really had it right. It's not the computer doing calculations. It's the passing of information from one computer to the next computer, from one location to the next location. Yeah.
If I could ask perhaps a very practical question. When I first started seeing models of climate change 10 years ago, there was a very clear attempt to predict changes in certain areas. The Peru would get drier, and North America would get hotter. Is that still being attempted?
Oh yes.
Or is that beyond what you can now predict? Because at some point you're going to get a tipping point where the change is no longer predictable.
There are two sides to your question. One is just without the nonlinear transitions, without the abrupt transitions, we can do finer, higher resolution, to give more information for a particular region. And when we do that, then we can take into the vegetation patterns in the region. We can take into, as I said, the mountains and the valleys, where the cities are. And so all those affect the bottom boundary conditions, affect the energy exchange, the moisture exchange. And so those have local climate. But when we go to the nonlinear part, the transitions, I cannot tell you, nobody can tell you today that in some year, I won't name, that that we would flip to the other side. That we're not in the position to do yet. We're just at the very early stages of thinking how to frame that question and what are the terms I need to have in my equations and what terms I really need to solve very well and what terms are not that important. We're still at the early stages of the abrupt transitions. So I can tell you, for example, another way of abrupt transitions is the methane cleft rates. There's a lot of methane on the seabed in the permafrost, and when it gets warm enough, then there may be bubbling out of methane. So there's a lot of that, and so there will be a lot of greenhouse gases in the atmosphere. But there's a lot of science that we still don't know. Is the methane going to be oxidized on its way up so that we get CO2 instead of methane? And a lot of things we don't know. The penetration of heat into the permafrost. So there are still research questions, a lot of research questions that we are beginning to know to ask. So I can't tell you when the abrupt transition would happen, but I hope we can do that in 5 years.
Is there some way where you can look at where the models are being published currently?
Oh yes, there will be the IPCC reports, the Intergovernmental Panel for Climate Change, United Nations report. Though all that will be, the 5th assessment report will be published later this year, and so you can see the latest update from 2007. But if you're interested, I can point you to the location where you can download all the model outputs, okay? And because it is United Nations, every model's included, but I can give you an opinion about which model does which processes well, and which model has invested more energy in the radiative transfer or in the vegetation or in the ocean circulation. So depending on the question you ask, there are certain models that I would go to and not others. And so each model has its strength and each model has its weakness. So, but all those are available now. If you want access to the last report, to all the output, you can have it. Okay, I'll just give you one link. And this is part of what we're doing by sharing all that information, by having students learn, okay, where the models do well, what the differences, because I keep saying there's only one atmosphere out there. So it's my conception, my conceptual idea of what are the processes that are important, and your ideas. So we now do model comparisons, intercomparisons, and so then we learn from the differences. Why do we have such a difference? Why do we agree? We agree because we all understand everything perfectly, or we agree because we're sharing the same code, because we know nothing. Okay, so there's a very elaborate international enterprise to understand the atmosphere, the observations, but also understand the models, which is a representation of what we think we know. So to look at the model differences is a lot of effort has gone into that. So this is how we go to the next generation of models.
Just a question on another level. Are there still denialists out there? You see a lot of the politicians or policymakers who say climate change is not happening. And at what are people coming around now to, on a bigger level, to seeing the effectiveness of work that you're doing, scientists like yourself and other people? In other words, it's seeing the reality there's actually something happening and not carrying on the status quo.
There will always be people who doubt whatever we do. And because there's only one atmosphere out there, for physicists, there's no repeat out there. So I will never, all I can hope for is when I do 100, when I run my model with 100 ensemble members, that the real atmosphere is somewhere in that pile. Okay, so when you say, when we have confidence, I'll be very, very sure, but I will never be 100% sure. Okay, because the data are lacking. There's only one atmosphere. So when we talk to people who doubt the results, or they look at the results and say, oh yes, no problem. We understand radiative transfer. We know what CO2 does. There will be some warming, but it isn't of the magnitude that we need to worry about. So that's when you look at the clouds. Okay, this is the clouds. The clouds going to damp all the amplifying effects. And so there is an uncertainty. But that's why I showed you the trend out 20, 30 years. Rather than debating what happened in the last 20 or 30 years, yes, there is natural variability. Okay. Yes, in the past, CO2 has been high, and the climate has been, and the temperature has been high in the geologic record. But those times, sea level was also very high. Okay? And when we look at the ice core record of the last million years, CO2 goes up. Okay, ice ages, CO2 was down. Okay, warm periods, CO2 was up. Those periods, to get into an ice age, we need to reduce the CO2. It won't happen when my foot is on the gas pedal. Okay, it won't happen when we're all using energy and it's going up. We may be overdue for an ice age, but it won't come. Okay, because the CO2, we keep CO2 up. So when we talk to people who doubt the results, we ask them, what would they do? I buy fire insurance for my house. I don't think there'll be a fire. Okay, I live on the Hayward Fault, on the earthquake fault. Okay, so you know in everyday life where your balance risk is, and what you do to avoid the risk. And so it's a judgmental call. And so what we argue all the time about is, you're thinking about now, or you're thinking about your grandchildren, the next generation and the next generation. So when you think in the future, then it's a totally different conversation. I'm not debating the past. Okay, let's talk about the future.
Thank you, Professor, for a wonderful talk. A much simpler and smaller scale question, maybe. I'm just wondering, is there any relevance in the greening of cities where you're trying to reduce the radiation of all the high-rise buildings, which is a beautiful thing to happen anyway?
It's a good thing to happen. And so there are lots of win-win strategies in this. And greening of cities, afforestation are all good things. What you have to, when I think about the greening of cities or planting trees, then I did in the model, I did a full-scale afforestation of the Arctic. And I put in deciduous trees in the model. And it turns out that because the trees transpire, there was a lot of melting of the permafrost. So the greenhouse effect kicked in. I melted sea ice. I evaporated more water vapor from the ocean, and I got a very large-scale warming. And so we did the same experiment in the mid-latitudes. All grasses, all crops are converted into deciduous trees. And so there is not, because there's a lot of water vapor already in the atmosphere. The greenhouse warming is not. The water vapor isn't big. Is not that big a deal. What happens is when we run out of soil moisture, then the land dries up. Okay, so then you have heating. The energy balance changes. So I think about transpiration as like sweating. Okay, if you're not allowed to sweat, you overheat. Okay, so when the trees run out of water, then the whole northern hemisphere warmed up, and now, when the whole northern hemisphere warmed up, then there's an energy imbalance between the northern hemisphere and the southern hemisphere. So the rain belt moved, and in the model, we dried up the southern part of the Amazon. Okay, so when I say it's a win-win situation, planting trees on the scale, nobody would do crazy things like what I did in the model. Okay, no, but the idea is to link all the processes together. So when it's greening, it's depending on what you replace with, whether it's dark asphalt or tar or what the albedo, how much sunlight is absorbed. But always when you water it, you use a lot of water. But when there's transpiration, then there's latent heat in the same way. Sweating, I cool, okay, by the evaporation. So it's a long-winded answer. It's a good thing to do. Okay, it may not be climatically significant, but it's a good thing to do.
May I just ask you a question? I might be incorrect in my assumptions on this, but I gather that the majority of the oxygen from the world comes from algae, and that there must be a critical temperature that you have been able to work out on the seas that algae would no longer be able to live.
I can give you an answer, but the biology is always smarter than the modelers or the mathematicians who have written equations. What we're concerned about with the algae, one is the acidification of the ocean. So right now we burn fossil fuel CO2. We burn fossil fuel and there's CO2 in the atmosphere. About a quarter of that goes into the ocean. So it's a very clear record that the pH of the ocean has been going down. The ocean's getting more acidic. So that's one thing. The temperature is another factor. And then the availability of macronutrients and micronutrients. So when we look at the algae, yes, there is a temperature at which, and you see the coral bleaching, and we can put, that's in the model, okay, where the algae would not survive. But what has always surprised us is other forms come in. And that's always the surprise. I can tell you, given the knowledge of 5 years ago, when I did the calculation, yes, the phytoplankton in my model did not do well when it got warmer. But they also didn't do well because the ocean is being warmed from the top, so it becomes more stably stratified. And so it's tougher to get nutrients up to the surface where there's sunlight. So there are many factors going in and not just temperature. So I would love to talk to you about the biology and the algae because it's now captured in a very simple way in the model. So what we do here is, even though it's captured in a very simple way, we have all the model results so that we can talk to the oceanographers, the biologists, and say, please, can you interpret this in a biological way for us? Okay, and what do we need to do better? So it's a very iterative process.
So I'm from the climate system analysis group, so you kindly referred to us earlier. And that's just to give you an idea of where this question is coming from. But I like the way you distinguish between weather and to a seasonal climate in particular as forecasting statistics. And I'm afraid this might be another open-ended question, but imagine we can't increase the computing speeds or can't get higher resolution, faster computers. Given that the need to give information to people to adapt to climate change, do you think we're running the right kind of experiments? And if we weren't able to improve computers further, would you change the way we do model experiments at the moment?
I think the dialogue that has to happen is happen in very small scale, but not on a larger scale. Is what are the users of the climate model results? What information do they need? Okay, what do we have to do better? And I don't think that we are running. They should tell us what experiments they want us to run, rather than us saying, "Oh, this is cool stuff for me." But the conversation is beginning, but it hasn't happened at the scale that we would like, is to have the users of the information for adaptation to come to us and say, we want you to run these experiments, and we want you to save your output in this particular fashion, the frequency and things like that. So that's the conversation I would like to see start or grow a lot more.
I just wanted to ask, our planet is a very intricate place, and we know that maybe it has a few tricks up its sleeves. Maybe, I don't know, something will happen and then it will change.
Yes.
And I just wanted to ask, if maybe we continue in this route that we're going in, what will eventually happen to our planet, maybe besides the climate change and stuff like that? What will eventually come to being of our planet? Will it explode, something like that?
No, it wouldn't explode. We have, in the past, seen warmer, where we're headed. In the past, there's been a warmer world, and I said higher CO2, warmer world, higher sea level. And so I can imagine the vegetation belts change, the rainfall and with the CO2 and with all of that. So I don't see the planet exploding. But what I do see, the planet is 4.6 billion years old. I think of us being on this spaceship. That's everything that we have for survival was there 4.6 billion years ago. I think I got a new water bottle, but it isn't that new. It's stuff. It's very old stuff that's reformulated. So the what I see in the future is how can we provide food? How can we provide fresh water for all the population, for all the people? And that's something that we have to worry about. So the planet will do its thing, okay? Because the planet will do its thing. It will be here. But it will be a very different planet from the one we know now.
Tonight we've been talking about the mathematics of planet Earth, but just for interest's sake, say we had the information, would these models be relevant to other celestial bodies as well?
Yes, the models have been used to study the atmospheres, the climate of Mars, the climate of Venus, and now I worked with a student on the atmosphere of Titan. So yes, this is the marvelous thing. You know, there's certain laws of nature that apply. Different forcing, different amounts of CO2, different mass of atmosphere, different everything. But we know enough to look at Mars and look at Titan and look at Venus and other planets. And I should say that when I show the chaos, you know, the red dots, you can think about that as civil unrest. Okay, a lot of long period of civil unrest, there will be a regime change. Okay, so it has been applied to the political situation. I asked Ed Lorenz one night whether it was U.S. politics, but you know, and he about a political situation, and he told me that no, the outcome of a particular election is not a chaotic transition, but the political process could be viewed as a chaotic process. Okay, so you can very. But the mathematics, this is the power of mathematics, okay? I look at those equations, I think about fluid, I think about convection and changing direction, but you can apply to, I'm sure that you have applied the chaos equations to many other applications.
You mentioned earlier in the talk that the model of temperature growth was a lot higher than anticipated when you actually measured it.
The emission is higher. The emission.
Okay, the emission's higher.
Yes.
And that you thought that we were
yes.
moving more towards the aggressive growth rate.
No, we're going above the aggressive growth rate.
Okay.
Yeah,
so,
we're going above.
So my question is, in that model, have you factored in population growth?
Yes.
And how much energy people are consuming?
Yes.
So how did you?
So those scenarios I didn't do. There's another group. We refer to SRES, which is a very uninteresting special report on emission scenarios. So economists, population, social scientists. So the world is divided into multiple regions, and so for each region there's a projection of population growth or decline. The economics, the energies, you know, whether it's fossil intensive or other energy sources, and whether the economic growth is global or there is consideration of sustainability. So that's why we have all those scenarios. So those are done by social scientists. And so then the scenarios of energy at the end, they're scenarios of population, of economic growth and energy requirements get translated into CO2 and methane and all those gases, and then we translate it into heating for the atmosphere. So I can refer you to all those studies. So what now, that was for the last round, for the 2007, the fourth assessment reports. For the fifth assessment reports, we are now talking about radiative forcing pathways, so it's more nerdy. So you can ask if we wish to stabilize temperature to 2 Celsius at the end of the century, what would be the composition of the atmosphere, how much CO2, methane, and everything else we allow. Okay, you can go from temperature to the forcing, and then to the concentration, and then back to the emission. So this is, we've been doing it forwards and backwards.
And in 30 years' time, what are the predictions for the population on the planet?
I will refer you, I don't have it top of my head. Yeah. Some regions actually declining, but a lot of growth.
Thank you very much. I'd like to find out about the models for removing excess carbon dioxide in the atmosphere. How effective are they? Like, if you can give figures, what percentage, to what extent are you able to remove in the models?
In the models, I put in the entire terrestrial ecosystem. So there's photosynthesis. Every 20 minutes there's CO2, the leaves. And so there is, I grow leaves, and then I watch them, whether it's cold or dry. The mortality of leaves, of ecosystems, of roots, and then the decomposition returning CO2 to the atmosphere. If, and this is a very big if, well, let me back up. In commercial greenhouses, they grow flowers in very high CO2 atmospheres because they have abundant light, they water, and they put in nutrients. So we know, given the abundance of all the other requirements for productivity, then the flowers grow, so you get bigger flowers. In the natural world, we think it could happen, but we are now beginning to understand, I talked about the water cycle, how much water, the soil moisture, but also the nutrient cycling. And so whether there is, yes, I wish the CO2 going up, the plants will continue to grow, but there's a nutrient limitation, and we're just beginning to have a sense of the global, not in my backyard, but global picture of the nutrient status. So whether the nutrients can sustain higher growth. In the ocean, we are again talking about nutrients. Okay, so the macro, so upwelling brings nitrates and phosphates, and then you need some dust, you need some iron input, and other micronutrients. And so there we have a first order expectation of what to happen, and that's in the model. But what is surprising is that when the oceanographers went out and they added iron to the ocean, in the Southern Ocean, a different species population came in. And so it totally disrupted the food web in a way that we had not anticipated. So this is why we kept, the planet is smarter than we are. And so we're just beginning. We've made a lot of progress. I hope I've persuaded you that we've made a lot of progress, but there's a lot more to learn and a lot more to do.
Right, okay. I think we have time for 2 more questions.
I don't know if it's appropriate to bring in James Lovelock and the Gaia theory at this moment.
Yes.
And the theory of the world re-establishing itself.
So Lovelock's the daisy world had black and white daisies. Okay, white daisies would reflect sunlight, and so when you change something, they would readjust themselves. Okay, so that the daisies would maintain the same temperature. Okay. That's fantastic if you're the species that survives. It's not so cool when you're the species that doesn't survive. But also in that scenario, you do not have the technology that is changing. Technology is so marvelous, and technology is giving us access to the energy, and that access is changing how the climate is systems. The climate is changing. So in the Lovelock world, there is no foot on the pedal, okay, that is forcing the CO2 to go up, so that the planet cannot adjust if we force it to go in one direction. So I don't know, we've never been there before. Yes.
I just want to ask is with respect to the feedback mechanism. You mentioned about the SEM index and then on how it's affecting a lot actually the source and sink of the CO2, especially at the poles. I just want to ask: is there a room to sort of the understanding of the feedback mechanisms in terms of the longer predictions that
oh yes
when you look at the sort of the worst scenarios and all that, like, is there sort of, are those the feedback, is that the sort of the best and the worst feedback mechanism that sort of can change the whole understanding of CO2?
Well, like what we find is that even if the plants could follow the CO2, if photosynthesis could increase at the same rate CO2 is increasing, suppose we could do that, then you still have decomposition, right? What the land can store, what the plants can store, is the difference between what comes in and what goes out. Okay, and so there's a lag, okay, because, you know, trees hang out for 30 years or so, and there's the soil, depends on where you are. In the tropics, the turnover time of soil carbon is about 5 years. It's about 200 years in the Arctic. Okay, so it depends, that difference between what comes in and what goes out is what is stored. So when it is warmer, yes, the CO2 may push this, you know, we want the CO2 to push the photosynthesis out, but the decomposition is also faster. You know, things rot fast, you know, when it's warmer. So I worked on that for a long time. You know, we have now the last round of the assessment reports. It was experimental at the time. So now we're trying to understand. But at the end of the day, the capacity of the land and ocean to store carbon decreases with warming. So that means that the warming is accelerating the warming, okay? And this is not in the results I have shown you, not in the movie I've shown you, in the generation of models that come after that. We find actually higher growth rate. So there, it comes back to water, not just the clouds and all of that, how much water there is in the soil and how much in groundwater. And I have a field experiment, you know, some trees in California, it's wet and dry. Okay, when the dry seasons come, you think all the plants shut down photosynthesis. No, not the madrones. So they peak in the dry season. So now we're trying to figure out where their roots are, where the groundwater is, and, you know, how they survive the dry season. And so we're hoping to learn something from all those experiments.
Well, join me in thanking Professor Fung for a wonderful talk. Thank you very much.
This is a picture from this is from the astronaut collection of photos.
Okay.
I don't need to explain
where it is.
Yes.
And I'd like to invite you to join us outside. There's something to eat and drink, and to continue discussion if you'd like to. Thank you. Thank you very much. It was wonderful.